In this video, we will learn about the periodic table of elements, how it's laid out, the names for its parts, and the neat ways that the position of elements on the periodic table indicates some of their properties. Chemistry is all about chemicals and how they react, but if you try to remember every detail of every chemical, you'd have a massive job on your hands. There are about 160 million recognized chemicals, and an infinitely greater number that we could imagine. Even if all we looked at were the named chemicals in use today, we'd still have too many to remember. However, all chemicals are made out of the chemical elements, and there's a limited number of these. We can use our understanding of the elements to predict the type of bonding in chemical compounds. We can then predict the reactivity and behaviour of chemicals that we haven't directly studied. However, 118 elements is still quite a lot. So, to help chemists out, there is a tool called the periodic table of elements, which helps chemists remember lots of details about the properties and behaviours of the elements. In this video, we're not going to look at the history of the periodic table. Instead, we'll look at the theory behind the modern periodic table and how you can best use it to become a better chemist. Each element is a type of atom or ion based on the number of protons in the nucleus. The number of protons in a nucleus determines the number of electrons needed to make it neutral and form an atom. The number of protons and electrons an atom or ion has determines how it reacts. So the number of protons in nuclei is really important. It's taken us a long time to isolate and identify the chemical elements we know now. What we have is an understanding of nuclei with between 1 and 118 protons. To start off our periodic table, we need to have some basic information about each element. A name and a chemical symbol have been given to each element. We can put these in a cell or box. The most basic piece of information we have about each element is the number of protons in the nuclei of that element. This is the atomic number. You'll usually find this above the chemical symbol, but sometimes you'll see it below or elsewhere. The other piece of information that's really useful is the element's average atomic mass. This is the average mass of an atom of that element in unified atomic mass units. This number is a measured property of each element, based on the abundance of the isotopes of that element on Earth. Not all elements have average atomic masses, because not all elements are found on Earth in large enough quantities for these measurements to be made. So what you may see instead is the average atomic mass of the most common isotope, or nothing at all. You need not worry about this in practice, because it's highly unlikely you'll be asked about an element which doesn't have a defined average atomic mass. If you're ever worried about telling the atomic number from the atomic mass, just remember the atomic number is always smaller than or exactly the same as the atomic mass. Once we have all the cells for the elements, it's helpful to put them in order by the atomic number of the element. But chemists also want to be able to compare elements based on how their atoms or ions react and how their electrons are arranged. For now, to keep things simple, let's only look at the first 20 elements, hydrogen to calcium. The first thing we could do when comparing these elements is look at the form they take when they are pure at room temperature and pressure. In their elemental form, some of these elements are gases, like hydrogen, helium, nitrogen, and so on. The rest are solids, and we don't happen to have any elements that are liquids at room temperature and pressure. There's no clear pattern here, so let's have a look at the elements that are metals and the elements that are non-metals. Metallic elements include lithium, beryllium, and sodium, and we don't include carbon, even though it's generally conductive for other reasons. All the other elements are non-metals, and we still don't have a particularly clear pattern. We'll have to dig a little deeper. The next candidate is reactivity. The element hydrogen is reactive. It forms compounds with other elements. For instance, hydrogen reacts with oxygen to form water, so we know oxygen is reactive as well. However, helium is the least reactive of all the elements, while there are many compounds for the elements lithium to fluorine. But, like helium, neon is unreactive. The elements sodium to chlorine are reactive, but argon is not. And finally, potassium and calcium are reactive, and we won't go further for now. what we've identified is a repeating pattern of chemical behaviour. But more importantly, we see similar periodic behaviour for the elements between helium and neon and those between neon and argon. We even see the same pattern continue beyond argon with potassium and calcium. And we even have a place for hydrogen, which is more similar to lithium, sodium and potassium than it is to fluorine and chlorine. A nice way of representing this information is to group hydrogen, lithium, sodium and potassium together in a single column or group. And we can do the same with helium, neon and argon. And we can do the same with the intervening elements, leaving a gap between hydrogen and helium because the data suggests that hydrogen should be above lithium and helium should be above neon. In this arrangement, elements left to right are still arranged by atomic number, but they're vertically aligned with elements that they share chemical behaviour with. The chemical behaviour happening in a set period as we increase atomic number is the origin of the name for the periodic table. Beyond calcium, things get a little bit more difficult. We have to make a big jump in atomic number to 31 to see the periodic behaviour of boron and aluminum continue. So we have another gap in our periodic table. In between calcium and gallium, we place 10 metals that have more to do with each other than they do with previous elements: scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. This is the first time we've encountered elements that behave the way these do, so these elements sit at the top of their group. Beyond gallium, germanium, arsenic, selenium, bromine, and krypton continue the pattern of their groups. The modern periodic table is built up through extension of these principles, although it's not possible to go through all the detail in this video. If we expand to include all known elements, we get a table like this. As we get closer and closer to the end of the periodic table, the difference in reactivity because of electronic structure becomes less distinct, so the electronic structure itself becomes what determines the position of an element on the periodic table. This form of the periodic table is known as the long form, and it's not often used because it's very wide and awkward to use. This is why this selection of elements is often moved below the table. This gives us the form of the periodic table we're most used to seeing. This form is easier to print and use. In this floating block of elements at the bottom, the element in the top left is lanthanum, so the elements along that row are called the lanthanides or lanthanoids. In the row below, the first element is actinium, so this row is known as the actinides or actinoids. Now let's go through some of the labels that are applied to areas of the periodic table which help us group elements by behaviour or electronic character. The simplest division on the periodic table is the line between metals and non-metals. In their elemental form, metallic elements tend to be shiny and electrically conductive, while non-metals are neither. Elements to the left of the periodic table tend to be more metallic, but hydrogen is an exception. It's a non-metal. To the right on the non-metal side of the boundary, we have elements like boron, silicon, arsenic and tellurium. As we get to the bottom right of the periodic table, elements become rarer and more radioactive, so the non-metal-metal distinction isn't as important. On the left side of this zigzag boundary, we have the metals aluminum, germanium and antimony. If you examine the properties of these elements close to the line, some elements seem to be like metals and like non-metals at the same time, and have properties that are in between the extremes of the two groups. These are called metalloids. Depending on who you ask and how specific you're being, some elements might be described as a metalloid, or as a metal or a non-metal. For instance, silicon is broadly classified as a non-metal, but it's more specifically classed as metalloid. On the other hand, germanium is more specifically classed as a metalloid, but also broadly classed as a metal. These are the elements generally considered to be metalloids, but some people include polonium and astatine, and even aluminum and carbon. Remember that these words are used to categorize elements, and therefore we'd expect some disagreement. The important thing is that you understand which elements you're talking about when you use these words. The next key word applied to the periodic table is group. A group on the periodic table is simply a column which is a collection of chemically or electronically similar elements. For instance, this column to the right is one group. Some of the groups are given numbers and we count left to right. Some people only count the 2 columns to the left and the 6 columns to the right, giving 8 numbered groups in total. This is useful when we're determining valency, but we'll come to that in a moment. The alternative scheme uses 18 numbered columns. Some collections and groups of elements have specific names. The metals in group 1 are known as the alkali metals: lithium, sodium, potassium, rubidium, cesium, and francium. But hydrogen, a non-metal, is not an alkali metal. The elements in group 2 of the periodic table are otherwise known as the alkaline earth metals. These are beryllium, magnesium, calcium, strontium, barium, and radium. Some groups don't have specific names, and some have lesser used names, like the group 15 and group 16 elements that are known as the pnictogens and chalcogens respectively. But the group 17 elements, otherwise known as group 7 elements, are generally known as the halogens. These are fluorine, chlorine, bromine, iodine, astatine, and tennessine. And lastly, the elements in group 18, otherwise known as group 8 or even group 0, are known as the noble gases: helium, neon, argon, krypton, xenon, radon, and oganesson. Each group has its own distinctive chemical character. For instance, noble gases are unreactive, while alkali metals are highly reactive. The group is useful for predicting the valency of atoms of elements in the first few rows of the periodic table. The early view of valency was the combining power of an element. Atoms of hydrogen have a valency of 1, while atoms of oxygen have a valency of 2. This means when hydrogen and oxygen combine to form water, we need twice as much hydrogen. These are the common valencies of atoms of elements in groups 1 and 2 and 13 to 18. However, valency is more commonly associated with the number of electrons in the outer or valence shell of an atom, in which case the valency of elements in group 1 and 2 is 1 and 2, and the valency of elements in group 13 to 18 are 3 to 8. The number of valence electrons in an atom are a large part of what determines how that atom reacts, so it makes sense that elements whose atoms have the same valency would have similar chemistry. Now that we've looked at vertical groups, let's have a look at horizontal rows. Rows on the periodic table are known as periods, which are collections of elements with the same highest occupied electron shell. That sounds more complicated than it is, so let me just explain. Every atom consists of a nucleus surrounded by a cloud of electrons. In a fairly simple model, we can describe electrons as occupying electron shells at various distances from the nucleus. An atom of hydrogen has only one electron, and we usually find that electron in the first electron shell. So hydrogen is to be found in the first period of the periodic table. Helium is also in period 1, because atoms of helium only have 2 electrons which sit in the first electron shell. Lithium, however, is in period 2. Atoms of lithium have 3 electrons, and there's only space in the first shell for 2 electrons, so the third electron goes in the second electron shell. We see something similar when we get to sodium. The highest occupied electron shell for sodium atoms is the third electron shell. This pattern continues all the way down the periodic table. In atoms of francium, the highest occupied electron shell is the 7th electron shell. So we can use the periodic table and electron shell diagrams to convert the period number and the shell number of the highest occupied shell. The electron shell model doesn't adequately account for all the electronic behavior of atoms of the elements, so we need to go a little bit deeper. Shells of electrons can actually contain what we call subshells, which contain orbitals of different shapes. The common types of subshell are S, P, D, and F. Shells further from the nucleus can fit more subshells. The first electron shell contains just an S-type subshell. The second contains an S and a P-type subshell. The third contains S, P, and D-type subshells. while the fourth electron shell contains s, p, d and f type subshells. You needn't worry about the impact of other types of subshell on the periodic table. We can group elements based on which type of subshell the valence electrons for atoms of that element are in. For instance, hydrogen and helium are said to be in the s block because the outer electrons of hydrogen and helium atoms are in an s-type subshell. And elements in group 1 and 2 are also said to be part of the s block. All the elements in group 13 to group 18, apart from helium, are part of the p block. In between the s and the p block, we have the d block, which in some interpretations also includes lanthanum and actinium. And the majority of the floating section below the table is the f block. You might see lanthanum and actinium as part of the f block. Generally, it's not that important a distinction when it comes to practical applications. The last important collection of elements we need to address is the transition metals or transition elements. Elements in this particular group are hard and dense in their elemental form and tend to form coloured compounds and multiple types of ion. Iron is a good example of a transition metal. It's hard and dense, and it's commonly to be found in coloured compounds containing Fe2+ or Fe3+ ions. Generally speaking, these are the elements considered transition metals, most of the D block and all of the F block. Some descriptions of transition metals exclude scandium and yttrium, and some definitions would include extra elements as well. But the most important distinction to make is that often only the transition metals in the D block are inferred when we say transition metal. When we're talking about transition metals in the F block, we'll say inner transition metals. Yes, it's confusing, but unfortunately it's the result of various different definitions of transition metal. Just be sure you know which definition you're using. So, to sum up the key points, the periodic table condenses lots of information about the elements. Each element is given a cell containing its atomic number, its element symbol, the element name, and the atomic mass. The elements are then arranged by atomic number and chemical and/or electronic characteristics. Elements can be classified as metals, metalloids, or nonmetals. The group and period can be used to determine the valency and the highest occupied electron shell for atoms of the elements. And the regions of the periodic table can be broken into S, P, D and F blocks, and we'll find transition metals in the D and F blocks.